this computer. So everyone, welcome to our CCNP class. I apologize again for all of our moving and things and stuff going on this summer. It's been a crazy summer. I've had two coworkers taken to the hospital by ambulance in the last 3 weeks from school. So it's and both of them are my direct supervisees. So it's been kind of a wild time. And then being gone last week was a bit of a craziness. Thank goodness they seem to both be doing okay. One of them had emergency surgery today, and the other is recovering, but won't be back till in August. So a little wild around here. But we are slowly but surely getting there. And I want to today talk a little bit about DM. Well, first off, let me open up questions. Any questions on the class, anything? I'm super behind on grading. I know that, folks. Remember, as far as our class is concerned, I do want to go over the requirements to successfully finish this class so that you know yourself what you need to do in order to finish this class and get your credits so that you can qualify for your CE credits from Cisco. 25 chapter labs of your choice. So 25 of the labs that we have. You do need to do the final exam with a score of 75 or higher. I will start turning that on for you. In fact, I'll turn that on in just a second. I'll start turning it on in case folks want to, for some reason, do it. Then the skills exam lab final, which, folks, that skills exam lab final is going to be inside of NetLabs once you log in. I would like for everyone to do the skills final. I actually cleaned a bunch of stuff up yesterday, which was a miracle. In our ENARSI, you'll see there's two different skills finals. There's SA1, SA2. I would like for everyone to do SA1. So do SA1, and that will be your skills final. Pick one of our pods and do it, and we will go from there. I have actually requested, and it will not be ready for you for this class. I apologize. I have actually put into the budget for another CCNP pod. One of the things I've learned by teaching CCNP is that these labs are very long labs, and we can actually typically take 4 pods, even 3 pods. We actually take, I think it's 7 pods for 50 students in our VMware classes and have no issues with people having enough time to do labs. But those labs are typically an hour and 10 minutes apiece. With these labs, they're very long, both Encore and these ENARSI. So I will warn you, if you plan on teaching this class, you're probably going to need more equipment than you would need for a typical CCNA class. So be warned. Have y'all noticed that, how much longer the labs are compared to other labs?
Yeah, they're definitely pretty long.
Yeah. Well, and it's a lot. I won't say a lot of it, but a good portion of it is erasing them and restarting them and putting those trouble tickets in. But every time you do that, that's a 5 to 7 minute process minimum just to let the router reboot. So they are longer than your typical CCNA lab. So again, I apologize if you've been trying to get time on the CCNP pods and they've been in use. We actually want to offer student classes, and to do that, I've already told the administration we've got to get more CCNP pods up and running to make that happen. But that's your skills lab final. That's what you will have to do. Under NetLabs, do the SA1 PMAP. So that's your skills assessment for this class. Any questions on that? Now, what I'll ask you to do is to upload or to do the lab, download it like normal, turn it into a Word document, fill in any questions that's on it. I don't think there are many questions on it, but if there are, fill them in, and then just upload it into our class where I have put in an upload in Canvas for our the final. If I hadn't put one in here, hands-on skills final, I actually put an upload in here. I'll do an assignment real quickly. I'll actually create one and put it here where you can upload it. Now, the other negative is this. Unfortunately, because this class uses Canvas as its primary area for you to upload and to get information, when the class ends, you lose access to Canvas. There's no way to extend that. Now, you will not lose access to our class inside of NetAcad, but you will lose access to Canvas. So if you don't have your 25 labs finished on the last day of class, what you need to do at that point is you need to email me those labs. You'll still complete them on NetLabs, and then you will bundle them together and you will email your completed documents to me. If you can get it all done by the end of class, awesome. If not, well, I usually give you a couple weeks after class to get caught up. All right. So questions on that?
Yeah, 25 lab means that some chapters they have more than one labs. They count as one, right? I mean, they count as probably
each
5.
individual lab is a lab.
Okay, yeah, that's what I
So
was
if you go in here and you see all these labs, you do 25 of these. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. There's about 37 labs, I believe. Each one of these is an individual lab. So Janaka, what I'm going to do is I'm going to go in and look and make sure you've done 25 individual labs.
Okay.
If you do troubleshooting 6 times, that doesn't count as 6 labs.
Understood.
Counts as 1. Okay.
Yeah.
But that means you don't have to do all 37 if you don't want to. Now, if you want to, and by the way, I am going to leave this class open after class ends on August 9th. As far as inside of NetLabs, I will not be turning off NetLabs. So if you want to continue to work in here as you practice to get ready for your ENARSI exam, you can do that. Okay. Typically, you end up with 6 months or so access after the class ends to be able to do labs. Just realize at any point I may say, hey, I need space and delete the class, but typically there's not a problem with you continuing to do labs past the end of the class. Does everyone understand why you will no longer have access to Canvas after August 9th? That's the last official day of class.
Yes.
Okay.
Yes.
Everybody's still good knowing what the O'Reilly database is, so make sure you're good there.
I have a question. I don't know whether I noticed that the labs, not on the net labs, the how do I say, the documents for the labs,
right,
and they have listed, like, for example, VRF, that I don't think it's even this class, but when I went to the net labs, it was not there. Is some of those labs are not, even though they are not in the net labs, though, even though those are listed as net academy documents or the labs, but they are not in the net labs.
This is all the VRF was in. I mean, there's
I think say ENCO.
Yeah, there's VRF. Yeah, there's just simply not a lab for it. Yeah.
Yeah.
We did VRF and we did some VRF in CCNP Encore. Yeah, we did definitely. Yeah. We did them in Encore.
But I tried to look at that lab, but I couldn't find it there also on the net labs.
Okay, give me a second. Because I'm pretty sure there's labs under Encore for VRF. It may not be the exact lab. Not all the labs in the curriculum, well, in the documents are in there. You may be.
It's an ENCO, like if you go, it's in the lab, like those student labs you can download, but not. I didn't see it here.
Look, then let me go see what we got here. Go find it.
Yeah, I was not sure whether that's something that on the net lab somebody has to enable or something like that. No, right?
All the labs are enabled for the that are in NetLabs. There's nothing additional that's available. Let me look at these files. Now remember, you've got to use the lab files inside of NetLabs when you do a lab, because they can be modified to work in NetLabs. Let me see here. I see the VRF Lite. That's the one you're talking about.
Yeah. That one I couldn't find on the net labs when I look at it. Yeah.
Yeah, we can implement VRF inside of what we've got easily. So I don't know why they did not put that one. Let me look at why the diagram. It's a diagram very different. Yeah, there's really no reason this couldn't have been built inside of NetLab, so I don't know why it's not.
It was not listed, so
yeah. It's a pretty simple VRF setup.
Yeah.
With R1 participating in the 2 VRFs.
Yeah, just going through those documents, that's even simple enough. simplify the implementation, but I was trying to like really do it on the lab and do troubleshooting and things.
Let me see if we couldn't. I was thinking, go back, hold on a second. Yeah, I don't know why it would not be here, honestly, because there's nothing in that setup that would be. I mean, nothing about that that's that weird in terms of the setup. I don't know. I don't have an answer. I don't have an answer for that because that VRF setup right there, there's nothing inside of NetLabs that should block that from working right there. Unless it's because of the way I see exactly why they couldn't build it. You see this A1, all of A1's set off of the D1, D2s down below there. And so mapping it to be in the middle like that would be impossible because we don't have a connectivity from R1 to A1. That's why that's happening. On that, what I would suggest is you get a hold of some real equipment and build it in your own lab.
Yeah, thank you so much.
Yeah, build that in your own lab. Okay, so let's now jump down here and spend just a little bit of time. We're not going to spend a ton of time on DMVPN because we won't get through it all today, but we're going to talk a little bit about it. Let's talk just a bit about DMVPN tunnels. First off, let's talk about just regular VPN tunnels. When we're setting up VPN tunnels, what has been some of the things we've done to this point? How do we set them up? Excuse me. You remember kind of the types of VPN tunnels we had? Because we've had, I need notepad. Come on now, notepad. We've had, well, if notepad wants to open, maybe not. Gracious. Leave it in my computer and not want to do anything today. We'll get Notepad++. All right. So we had remote access VPN.
Site to site.
And site to site, correct. Now, site to site, one of the things about site to site that we talked about is you typically in site to site, well, not just typically, but almost always have full control of both sides. In other words, you know the endpoints for both sides of your tunnel. So you set up this branch office goes to this central office. Now, remote access VPN is much more like what we're going to talk about with DMVPN or dynamic multipoint VPN, because you don't have control of one of the endpoints. So on one endpoint, endpoint at a remote access is usually a host device. And we put software on it so that it can, quote, dial in to a central area. Well, that's great. And so what they wanted to do is they wanted to say, can we take some of the ease of a site to site, excuse me, a remote access VPN, so take some of the ease of that and transfer it into how we deal with a large number of different endpoints that need to connect to a hub. That is how they came up and built this idea of DMVPN. All right. So as we look at DMVPN or dynamic multipoint VPNs, it's going to look at the different components that are used to create a DMVPN, which one of those are GRE tunnels. And we'll also eventually get down into, in the next chapter, how to secure it with IPsec tunnels or IPsec over these tunnels. But we're going to look at GRE tunnels. We'll look at next hop resolution protocol, which is used in order for clients to be able to find a DMVPN hub or a DMVPN server. And we'll talk about this dynamic multipoint VPN and how that works. So first thing, GRE. GRE is a open generic route encapsulation. It is a way to just create a tunnel across a network so that the endpoints have no idea that they're passing through multiple things in between them. Originally used as for non-routable protocols like IPX, DECnet, SEN, AppleTalk, those types of things. You could put them through. I think you could put AppleTalk through. I can't remember right now off the top of my head, but I'm pretty sure you could. But with multi-point GRE tunnels, DMVPN allows for what's called dynamic routing, and it allows for the tunnels to be built and tore down very easily because you set up endpoints that are servers and endpoints that are clients. Now, a basic tunnel is you literally create a tunnel endpoint, say tunnel source, tunnel destination. You can create a tunnel, and in this case, R11 and R31 believe they are directly connected to one another across the GRE tunnel. Now, obviously, there has to be some way for those two devices to actually talk to each other across the physical network that is underneath this virtualized GRE tunnel. And I say virtualized tunnel, but it really is just a virtualized tunnel. An overlay tunnel or overlay network is also another term that's sometimes used in it. You can pass things through this tunnel that would not normally be able to go across an open network. So it's interesting in how this works. The other thing that's also interesting is a GRE tunnel is not by default secure. So everything that goes into the GRE tunnel, even though it doesn't even know it's going through 15 routers or 15 hops, or in this case, a single service provider router, it's open. It's not being encrypted. Now, there are ways to do GRE inside of IPsec, and there's ways to do IPsec inside of GRE. So there are ways to do that we've studied. So this is pretty simple. You'll notice R11 goes to R31 via the tunnel, the GRE tunnel, and it believes it's literally just 2 hops away instead of going across the entire X number of hops that would be in the middle. GRE tunnels are very simple. Interface tunnel, tunnel number. Then you do your tunnel source, you do your tunnel destination, and then you do have an optional, you can tune the bandwidth, you can do your keep alives. You can also change the MTU if you so choose to. Sometimes that's necessary depending on what's going through it so that it doesn't exceed the MTU of the pass along the hops. But here's an example of interface tunnel 100. By the way, those numbers do not have to match on both sides. It's a good best practice for them to do so, but they don't. There's the IP address of the tunnel. There's the keep alive, or the MTU and the keep alive. And then this tunnel source is gig 01. Tunnel destination is this 172.16.31. So that would be the IP address on R31 and vice versa. So they now can go across one another, and you have the ability for R11 and R31 to believe they're directly connected to each other. All right. Very simple, easy. We've done that before. Now, next top resolution protocol is a way for hosts on what are typically non-broadcast multi-access networks like frame relay or ATM networks to be able to do resolution, address resolution on those types of networks. And it has on it NHRP clients and servers. DMVPN takes these multicast GRE tunnels and uses that as a way for NHRP to allow you to have inside of these messages the ability for a client to register with a hub without you having to define an actual full IPsec connection between those two. In other words, instead of you having to do an entire VPN connection between all of your client endpoints, all of your branch offices, you create your hub, and then you configure it to accept connections from your clients using certain parameters. And all of that is handled by this next top registration protocol, or resolution protocol. So some of the common messages here are showing those. You do have to be careful sometimes with NAT, so you have to be able to do NAT workarounds with DMVPN, but it has that, it can do NAT transversal. It's built into DMVPN. So DMVPN, instead of having you have to go and build manually the VPN tunnels for every endpoint, if you build your hub, once you built your hub, the sites can initiate a persistent VPN connection to the hub. And the good news is the sites don't even have to have a static IP address. If we remember, if we go back to our site-to-site VPNs, you are expected to have full control. So you're expected to have static IPs on both sides. Okay, static IP addresses are expected on both sides for that, for a site-to-site VPN. With a dynamic multi-point VPN, you would have a static IP address on your hub, but your spokes could use dynamic IP addresses. So you can save money by using a business DSL or something that's cheaper than having an actual connection that has its own static IP address. DMVPN hubs do not require additional configuration when other spokes are added. And we're going to learn too that depending on how you set up your DMVPN setup, there's a way for all communication to go through the hub, which by the way, that would let you control it with the firewalls at the hub and your security information at the hub. But if for some reason you want the spokes to be able to talk directly to one another, there is a way through DMVPN to have them register with the central spoke or central hub, and then also have the ability for that hub to say, oh, you want to speak to the other spoke, create an automatic VPN tunnel to that other spoke and talk directly to it. That is all without you having to manually go in and configure site-to-site VPNs between all of your different branch offices. Okay, so it's very scalable. One of my students did this, oh God, it was probably 15 years ago. They were working for a bank, and they contacted me about DMVPN, and we discussed it and what they were doing. And very similar to what they've done is they set up the central office as the hub. All of the branches were clients, and they were registering with that NHRP protocol and establishing automatic connections back to the central office. DMVPN can use IPv4, IPv6, and even MPLS as the overlay, or the transport network, either one. So you can do either one. It does support multicast traffic to flow across the tunnels, which is big, because that means it will support some of our routing protocols that we've not been able to support before on a non-broadcast multi-access network, because they do not typically support multicast. And you can do connectivity behind NAT. So they do have the ability to do the ability to transverse NAT. And then it's just built on standard blocks. It's built on GRE, Next Hop Resolution Protocol. It's built on IPsec. So it's not anything that's using some new spooky new technology. It's built on technologies that we already know work well. I'd say NHRP is the newest of the technologies with what's going on here. So it was released in 3 phases. To begin with, phase 1, and this is the one my student was working with years ago, was just zero-touch deployment for VPN sites. Create a hub, set it up with all the parameters, set the clients up. The clients would then, as they need to connect back to the central office for the hub for whatever reason, they would automatically create a VPN tunnel back to the hub, and all traffic from the spokes had to transverse the hub. They could not go from spoke to spoke. The next phase they worked on was phase 2, which is the ability to do both connect. You can still connect to the hub, obviously, but the hub could say, oh, you're wanting to talk between site A and site B. Well, instead of bringing that traffic through me, why don't you just create a dynamic tunnel between A and B, because that would save you not just bandwidth, but it could possibly save you in processing time, because it's not having to come all the way up to the hub and then come back down. So that was phase 2, spoke to spoke. And then last, they actually developed and have developed what's called hierarchical tree spoke to spoke. So by looking at the routing table, you can end up with the hub can allow spokes to become almost like mini hubs in some ways, and we'll see that as we move through here. So here's phase 1, very simple. Everybody's got to talk to the hub. All right, no problem there. Everybody knows that. It is a spoke to hub tunnel. Those tunnel, and they say they're persistent. So they are typically persistent. They come up, they're set to stay up unless they need to be torn down for some reason. But even though they're persistent, they are not something that you have to manually configure. So if you bring on 10 more spokes, you don't have to sit and manually configure it. You just put the typical DMVPN configuration with the parameters onto the hub or onto the spoke, and the hub will allow them to create a tunnel. In phase 2 and 3, you see that the spokes can create dynamic connections between them, send the information that needs to go between the spokes, and then tear that VPN down. So phase 2, phase 3, you'll see here that phase 2 and 3 with DMVPN multi-level, you can see how in phase 2, you've got the general hub telling them to go down to the spokes, and then you can have regional hubs instead of the global hub. And the same thing here with these regional hubs with phase 2 and 3. The regional hubs are able to tell the spokes they can talk directly to one another, even across regions. So we don't really do a whole lot with phase 2. We do more in this chapter with phase 3. So types of configurations, obviously the hub and the spokes. So depending on the role, the hub is set up as the next hop server, and the VPN spokes are set up as the next hop clients. The spokes will be configured with the hub's static IP address. That's why the hub has to have a static IP, but the spoke can be dynamic or static. And for us in the book, when we're reading it, spoke router and branch router are interchangeable, as are hub router and headquarter or data center router. So they're being used. So here we see DMVPN tunnels. We got a non-broadcast multi-access transport, which could be frame relay, could be ATM, could be whatever, probably frame relay more than likely. And so we are wanting, in this case, to run something like EIGRP, which requires multicast, and we can operate that on the inside the DMVP tunnel, and then it can actually exchange this 172.16.0.0, whatever it happens to be, .x.x, through the DMVPN tunnel, which we would not be able to do otherwise, because if we were in a non-broadcast multi-access network, it would not support multicast. So we could not run EIGRP as a routing protocol. So creating a hub or DMVPN on a hub, you create your tunnel interface, create your source, and then you configure your MGRE or multicast GRE tunnel or multi-point GRE tunnel, information on the parameter on the hub. So tunnel mode GRE multi-point. You put your IP address for the tunnel. You enable a unique DMVPN tunnel virtual interface. So you got to put an ID on it. So next hop resolution protocol ID. And then you also can have it optionally support multicast. Probably will, because most of the time you want multicast to be able to go across that. If you're using phase 3, you have to use the redirect, NHRP redirect. That allows the hub to redirect the spokes to talk to one another and develop or to build VPN tunnels between one another. Okay. And the spoke will have to share between those two, the hub will have to share between those two spokes the dynamic IP addresses of those spokes if it is, if they are dynamic. And then you also can set your MTU and your TCP adjust size if you want a different maximum segment size. Now, for the spoke configuration, you do a tunnel interface just like we did before. Tunnel source, tunnel destination, which would be the hub, and then allocate an IP address for the tunnel, allocate the next hop resolution protocol ID, which needs to be unique across all of your different entities. Put a tunnel key, that's optional if you've set it up on your hub. Okay, so if it's defined on the hub, it's got to be defined on the routers. Now you may want to do that. Obviously, I would do that in the real world for security reasons. All right. Then specify next hop servers using this next hop server address, and you actually can have multiple hubs if you want to. So you can actually set up multiple hubs in case one goes down if there's a problem. Tunnel bandwidth, and then the MTU and the maximum segment size, just like we did on the hub itself, so on our spoke. So here's our hub. We do interface tunnel 100. We do, and by the way, the numbers again don't have to match, but I would suggest they do just for simplicity's sake. IP address, NH map multicast dynamic, network ID 100, TCP, must be a local. I may have been wrong with that, y'all. I'm sorry, I may have misread that. Yep, that's a local command. I'm sorry. The network ID is local. It does not have to be unique across everything. Misread that one. But you've got your local ID for that tunnel. If you had multiple tunnels, you would need a different ID for it. And then you've got your segment size, source, multi-point, and then you go down into your other tunnel and you will see that you have your next hop resolution protocol, next hop server is the IP address of the tunnel interface on your hub, and non-broadcast multi-access that allows you to do multicast, okay, which says basically the tunnel destination is 11, and that would be an actual IP address that's on the device itself. And so all of your different spokes could be set up to connect to your hub. And then they just connect. Notice we did not set up IPsec, IKE, none of that's not there yet. We didn't set up ISACAMP. We didn't set up the things we normally set up for a typical IPsec VPN tunnel. This is just a GRE DM VPN tunnel. We're going to talk about next chapter how to secure these tunnels with IPsec. Questions? Okay. So we can look at our tunnel interfaces, and it's just like a GRE tunnel. Typically, it's up, down, tunnel roll. This again, we'll talk about IKE and IPsec next chapter. When you get into chapter 20, it talks about how to actually secure a DM VPN tunnel. So here's some of our statuses. Tunnel is up, tunnel source destination, and you can see the peers. Show DM VPN detail, provides the local tunnel, the non-broadcast IP address, the tunnel health. And so that's the address. This non-broadcast multi-access address would be the actual physical addresses that are on the underlay network that this tunnel is running on. All right. So here we see tunnel on R41, which is a spoke. Tunnel is up. You've got your tunnel source, tunnel destination. Which again, that is the true actual IP address on a physical network interface. And then this would be the source of it. And then down here you see you've got our next hop server and its connection to it. So we've got a peer, we got it up, and target network. So we've got a GRE tunnel running across these two. All right, here's looking at the cache, show IP, NHRP. So showing that we're unique registered used. So it's a dynamic tunnel that is up. So instead of creating every one of our tunnels individually, we can do this as a hub and spoke setup. The big difference between phase 1 and phase 2 or phase 3 DMVPN is using this redirect command, which allows the spokes to then create a tunnel between themselves instead of just to the hub. So you'll notice it's really the big difference here is NHRP redirect, and then on the spokes we do NHRP shortcut and GRE multipoint, and that is because now the spokes are no longer just a point-to-point back to the hub. They have to have the ability to do a multi-point GRE tunnel because they've got to be able to create a tunnel both to the hub and to other spokes when they get redirected to those spokes. Pretty simple, I think. I mean, it's not really an extremely hard thing to see at. We can also have passwords in next hop resolution protocol. We can set up authentication, and probably a good thing. Here's our spoke to spoke. So packets flow through the hub in a traditional hub and spoke manner until the spoke to spoke tunnel has been established in both directions, and then it will flow across using the redirection. It will start going in the more optimal path in the spoke to spoke tunnels. So what happens is, if there's information to go between two spokes, until the tunnel between the two spokes comes up, that information will go to the hub and be redirected down to the other spoke. Then as soon as the hub sees, or actually the devices see, there's a better route, in other words, the tunnel from spoke to spoke comes up, then that information will be redirected to go back across the spoke to spoke connection instead of across the other. So you'll see here, it went across the hub until the tunnel was established with the spoke to spoke. And as soon as it did that, then it went directly, which saved it a hop and made it more efficient. Which, if your tunnel endpoint was 10 hops away and your spokes were only 2 hops from each other, that would save you much more than just this example network of a single. And this shows you a spoke DPN tunnel. Spoke connects to the hub, and then you get your request. The hub's going to look at it, send another request, the data packet's going across, and then eventually what will happen is you will get a full next hop resolution protocol, or excuse me, next hop, resolution protocol between the two hubs. Can't talk to y'all. Two spokes, and the spokes will then connect to each other and send information directly. All right, so that's pretty simple there. Of course, next hop resolution protocol does place things into the routing table. Depending upon how also you've set up your routing inside of your environment. Are you routing across the DMVPN tunnels? Are you not? It does take care of that. And we've got summarization here, which is similar to regular summarization. All right. Here's an example of a common problem. It's called recursive routing problems. So if a router tries to reach the remote out router's encapsulating interface, the transport IP address, through the tunnel, in other words, it should know about the underlay network, but if it for some reason tries to learn about the underlay network through the tunnel you're establishing, you end up with what's called recursive routing, and that can cause issues with the ability of your routing table to be created, and also not only created but also to be most efficient. If you accidentally add the network, the underlay network, to your overlay tunnel routing protocol, now you've suddenly got that inside of EIGRP, which is supposed to be only inside your overlay tunnel, not being used for your transport. Now you notice I told you that R11 and R31 still had to have a way to connect to each other. Especially when you're doing GRE tunnels, they had to have some way of knowing where they're at. Well, in this case, in the underlay or the base network, they were using OSPF as the transport. Well, accidentally, the admin added the 164 network to the EIGRP, which is inside the tunnel. And because EIGRP has a better administrative distance than OSPF, it went into the route table. And so that's going to cause a problem with it being able to find its way for the two devices to be able to actually connect to each other, because the tunnel needs to exist in order for R11 and R31 to share this route information. But the item they're trying to use to create that relies on the tunnel. So it's a chicken and egg type thing. You've got to have a tunnel established for EIGRP to share the 164 network, but that tunnel's not up. So suddenly you get issues with your routing. Okay. Questions?
I'm good.
Have y'all done the labs on these? Have you been able to do any of the tunnels, GRE tunnel?
Not yet.
Actually, yeah, I did the I mean, that lab only has the GRE IP version 4 and IPv6 information only, and it
Yeah.
doesn't really have the DMBPN or anything.
Yeah, it doesn't have a lot of DMBPN stuff.
Yeah.
It's a very easy lab for the GRE
Yeah.
tunnels. It's a simple lab, just creating
Yeah.
GRE tunnel. But
It's
really,
mainly the GRE.
yeah, and but DMBPN really it relies on that GRE tunnel, so it's not that much of a stretch as long as you know how to do GRE. So let's take a peek here real quick. I want to see. How deep we got it. Oh my. So you do have to be able to configure and verify a single hub. So basically, when we're looking at our setup, what I would focus on would be that the parts of our discussion where we were doing the single hub and the spoke. So phase 1. And then looking at the spoke, which really is just the redirect and the GRE multi-point on the spokes themselves. All right. Anybody else from our first class been able to go and take? I'm sorry. Yeah, there's a lot of feedback. I see it. Is there anybody from our first CCNP class been able to take the exam yet? I know, like I said, I sent out Debo passed, which was very cool. If you do happen to take it, let me know, and I'd love to know how you do. It's always fun to know when students do well. So I'm gonna